Welcome back to the Deep Dive. Today, we're going way back to the early universe, trying to figure out a mystery that's really been stumping scientists. How did those supermassive black holes, the ones billions of times the mass of our sun, form so fast after the Big Bang? I mean, it just doesn't seem like there would have been enough time, you know?
Right. It's a real head-scratcher.
Exactly. And you sent over this really interesting article about a new discovery. It seems like we might finally be getting some answers.
Yeah, it's pretty exciting stuff.
It's all about quasars, these super bright beacons powered by those supermassive black holes we were just talking about. And they use these incredible space telescopes, XMM-Newton and Chandra, to observe them.
Yeah, that's right. The article focuses on observations of 21 of the most distant quasars we've ever seen, which is amazing because we're seeing them as they were less than 1 billion years after the Big Bang. And the observations are kind of challenging what we thought we knew about how black holes grow. It all comes down to something called super-Eddington accretion, which basically means they were growing way faster than we thought was possible.
Okay, so the article mentions X-rays a lot. What are the telescopes actually seeing?
Well, think of the X-rays as like a window into the area right around these black holes. They're showing us what's going on with this incredibly hot gas in what's called the corona, the region closest to the black hole itself.
I see. And the article mentions some pretty intense winds, too. What's the deal with those?
Oh, yeah. Picture these incredible winds of matter just blasting out from the quasars, thousands of kilometers per second. And what the researchers found, which is really interesting, is this connection between how fast the winds are moving and the temperature of the gas in that corona.
So faster winds means a cooler corona? I'm not sure I follow.
I know, right? It seems counterintuitive. But what it suggests is that these black holes were gobbling up matter at an insane rate, way beyond something called the Eddington limit.
Eddington limit?
Yeah, imagine there's this cosmic speed limit for how fast a black hole can devour matter, based on the outward pressure from all the radiation it's blasting out.
Wait, so are you saying these black holes were breaking the cosmic speed limit? Defying physics?
Well, not defying physics exactly, but exceeding a limit we thought was pretty solid. And that's where super-Eddington accretion comes in. It could be the answer to how these supermassive black holes got so big so fast in the early universe.
That's wild, but how can they be so sure this is happening just by looking at X-rays?
Well, they saw the same pattern in all 21 of the quasars. The ones with these weaker, lower energy X-ray emissions, meaning the corona was cooler, those consistently show the super-fast winds, which points to this super-Eddington accretion. And the quasars with the stronger, higher energy X-ray emissions, they had slower winds.
Huh. Like a fingerprint, almost.
Exactly. It's like a signature.
It says here that they collected something like 700 hours of data from XMM-Newton for this thing they're calling the Hyperion Project. Talk about dedication. What else can we learn from these ancient behemoths?
Well, one of the most exciting things is, it's like we're opening this whole new chapter in the story of the universe, you know?
Yeah.
It's not just about figuring out what happened billions of years ago. This research is like setting the stage for future discoveries, too.
No, totally. Like those missions they mentioned.
Yeah.
Athena and HXIS and Lynx. They're the next generation of X-ray telescopes, right?
Exactly. And with those, we'll get even clearer, more detailed pictures of what's going on around those black holes.
It's kind of mind-blowing to think about. The technology we're building today might help solve mysteries that have been around since, well, practically forever.
It is pretty amazing.
So we've got these quasars blasting out X-rays, these supermassive black holes breaking the cosmic speed limit, and this whole super-Eddington accretion thing.
It paints a pretty crazy picture of the early universe.
Yeah, and it makes you realize just how much we still don't know.
Absolutely. I mean, super-Eddington accretion is a really cool theory, and it seems to fit what we're seeing, but it's still just one theory, right? There could be other explanations out there that we haven't even thought of yet.
That's what I love about this stuff. It's like we're always peeling back another layer of the cosmic onion.
I like that.
And with every layer, we get a little closer to understanding how everything works. It makes me wonder, what other secrets are those ancient quasars hiding? It feels like we're just scratching the surface.
Oh, for sure. Think about it. Every one of those quasars is like a time capsule, holding all this information about the early universe.
Whoa, yeah.
We can learn about how galaxies formed, how the universe itself evolved, not just about black holes. It's a pretty exciting time to be studying this stuff.
You're telling me. Actually, you know what else I thought was really interesting? That part of the article that talked about another theory for how supermassive black holes form.
Oh, yeah, you mean direct collapse.
Yeah, that's the one. Can you tell us a bit more about how that works?
Sure. The direct collapse idea is really fascinating. It basically says that in the super early universe, you had these areas so packed with gas and matter that they could just collapse straight into a huge black hole, skipping the whole star formation step.
Whoa, so instead of starting small and gradually getting bigger, these supermassive black holes could have just popped into existence already fully formed.
Exactly. It's a pretty wild idea, and there's still a lot of debate about whether it could really happen or not.
Of course.
But it just shows how complex all of this is, you know?
Yeah. Like, we need to keep an open mind when we're talking about the early universe, right? There could be all kinds of weird and wonderful stuff going on that we haven't even imagined.
Absolutely. We're learning new things all the time, and every new discovery leads to even more questions.
That's the best part. So we've got quasars blasting out X-rays, supermassive black holes growing super fast, and this whole direct collapse idea on top of that. It really makes you wonder, what else is out there? You know, what other crazy things are waiting to be discovered?
I know, right? It just shows you we're only just starting to understand how the universe works. And that's the beauty of science, you know? Always pushing the boundaries, exploring the unknown.
Totally. It's like the universe is just daring us to keep asking questions, keep digging deeper, and see what we can find.
Exactly. And that's where you come in, you know. We've been talking about all this incredible stuff, these supermassive black holes, quasars, super-Eddington accretion, direct collapse. But now we want to hear from you. What really stood out to you in this research? What piqued your curiosity?
Right. Like, what are you still wondering about? What questions are you left with after this deep dive?
Maybe you're thinking about the big picture, you know. How does this research change our understanding of the early universe? Or maybe you're just fascinated by the idea of black holes growing at these insane speeds.
It's really mind-blowing stuff.
It is. And whatever you're thinking, we want to hear about it. This deep dive is just the start of the conversation.
Yeah, exactly. So keep exploring, keep asking those questions, and never lose that sense of wonder.
Because the universe is full of mysteries just waiting to be uncovered, and who knows? Maybe you'll be the one to make the next big discovery.
Thanks for joining us on this journey to the edge of the universe, and until next time, keep looking up.